Dear students, under the lecture series of graph theory, here we have lecture 10. This is a very significant theorem in the examination point of view. That is, the theorem states that the maximum number of lines or edges among all p-point graphs with no triangles is p square divided by 4. So, the maximum number of lines among p-point graph. So, the number of vertices in the graph is p. Then, the number of possible edges will be equal to p square, the integral part of p square by 4, and with particularly no triangles. That is, in a graph, if there are no triangles, then the maximum number of lines possible for a p-point graph is integral part of p square by 4. Before proving this theorem, let us try to understand what is this integral part of p square by 4. And for example, if you have a number, that is, if you have 2.36, then the integral part of this number is equal to 2. That is, it will be the greatest integer not exceeding this number. What will be the integral part of 4.6? Obviously, it will be equal to 4. So, it is the greatest integer not exceeding 4.6. Not exceeding 4. So, it will be equal to 4 because this is the integer. So, similarly, when we have p points in a graph, then the maximum number of edges, possible edges, will be equal to integral part of p square by 4. This theorem can be easily verified for values lesser than or equal to 4. That is, for all those values of p lesser than or equal to 4, easily we can verify. But as the vertices keep on increasing, the verification becomes difficult, in which case we will be proving this theorem generally. So, first we will see what happens when p is equal to 1. So, if you consider a graph where the value of p is equal to 1. So, if you see, what is p? P is the number of points. So, if there is only one point in the graph, how will the graph be? So, it will be like this. So, how many edges do this graph have? The number of edges is 0, because if there is only one point, you cannot form any edge. So, the number of edges is equal to 0. We are excluding the loop and the multiple edges. We are considering only graphs without loops and multiple edges. So, there is no edge possible when p is equal to 1. So, that is what is the integral part of this? That is, we will take p square. P is 1. So, 1 square is 1 divided by 4, which will be equal to some 0.2. So, what is the integral part of this? This is equal to 0. So, therefore, this is the value of q. That is the maximum number of lines with p point, that is p is equal to 1, is 0, which is q equal to 0, which we saw by taking an example of a graph. Now, we will consider p is equal to 2. That is, there are 2 points. So, what are the possible number of edges? So, if there are 2 points, the maximum number of edges is 1 only. So, q is equal to 1. Let us verify from this. That is, we will consider the integral part of p square by 4. P square is 2 square by 4, which is equal to integral part of 2 square is 4 by 4, and that is equal to 1. So, if you see, q is equal to 1. We have arrived at it. So, this result is true when p is equal to 2. Now, if we take p is equal to 3, what will be q? So, if for example, if you are taking 3 points. So, now what are the maximum number of edges possible for this? You can have an edge like this and you can have an edge like this. Or if for example, if the points are like this, the edges can be like this also. Or you can also have, so if it is like this, you can also have the edges to be like this. So, these are the possible number of edges. But if you see the maximum number of edges, how many edges you can have? You can have the value of q to be equal to 2. So, we will check by the theorem also. P square by 4. What is p? 3. So, 3 square is 9 by 4. And what is the integral part of this? This is equal to 2. So, therefore, if you see, we have arrived at q is equal to 2. So, the theorem holds for p equal to 3 also. For example, if you take P is equal to 4. And why I considered these to be maximum number of edges? If I draw another edge like this, it will become a triangle, but there should be no triangle. That is the condition that we have. So that's why we have drawn these many edges. Now for P equal to 4, we will see what is Q. So you will have P equal to 4 points. So the maximum number of edges, so it can be like this, it can be like this, and it can be like this. And if you see, there is an edge here, 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 3 edges, and it can be like this also with these points. But you cannot join like this because it will form a triangle. If you join like this, it will form a triangle. So you cannot do that. So what are the maximum number of edges possible? 1, 2, 3, 4. So the maximum number of possible edges is 4. We will check with the theorem also. So P squared by 4, P is 4. So 4 squared by 4, which is 16 by 4, and that is equal to 4. Hence by the theorem also it is true. So we can easily prove the theorem for values lesser than or equal to 4. For all values of P lesser than or equal to 4, the theorem holds. Now therefore we have to prove the theorem for all those values greater than 4. So that we will write first. So therefore I have written that the theorem can be easily verified for P lesser than or equal to 4, which we have already done. Okay, so we are going to prove the result for P greater than 4. So all those values which are going to be greater than 4. Now what we are going to do, this P we are going to segregate as odd vertices and even vertices. So odd P and then even P. So we are going to segregate it as odd and even, and we are going to prove the result separately for odd and then separately for even. So let us write that. So I have written that we will prove the result separately for odd P and for even P. So let us proceed with the proof. So first the part 1 will be for odd P, that is odd number of vertices. When P, the value of P is odd. How will the odd numbers be? It will be like 2n plus 1, 2n plus 3. These are the generalized form of odd numbers, because if you give any value for n, it will be an odd number. For example, if you give n equal to 0, it will be 1, which is an odd number. N equal to 1, so 2 plus 1, 3, so which is an odd number. N equal to 3, if you take 6 plus 1, which will be an odd number, because 3 2 times is 6 plus 1 is 7, which is an odd number. Similarly, 2n plus 3 is also an odd number. So these are the general forms of the odd number. So the idea of the proof is going to be by the method of induction. So what we are going to do, we are going to assume the result is true for odd number, that is 2n plus 1, that is 2n plus 1 number of vertices. And we are going to prove that the result is true for 2n plus 3. So till 2n plus 1, the result we are going to assume as true. And then we are going to prove for 2n plus 3, which is known as by the method of induction. So we will be proving it is also true for 2n plus 3. So first let us assume that the result is true for 2n plus 1 number of vertices. That is when P takes the value 2n plus 1 or lesser than that. For P, so for P, all P lesser than or equal to 2n plus 1, we are going to assume the result is true. So I have written that here. Let us assume that the result is true for all odd P lesser than or equal to 2n plus 1. So we are going to prove that the result is true for a particular value P, which is equal to 2n plus 3. Now in order to prove that, we are going to take a graph G, and we are going to take that it has P number of vertices and Q number of edges, with the particular value P to be equal to 2n plus 3. So we want to prove the result for this value. So we are going to take it as 2n plus 3. And very importantly, from the assumption of the theorem, we have no triangles in the graph. So let us consider all this. Now first, if Q is equal to 0, that is if there is no number of edges, then obviously Q is already lesser than or equal to P square by 4, which we already saw. So we are going to consider all those values of Q to be greater than 0. So let us put it in words. Now after making this, that is after taking Q to be equal to 0, we see that Q is lesser than or equal to integral part of P square by 4. So therefore we are going to prove the result for all those values of Q greater than 0. So first what we are going to do is we are going to assume a pair of adjacent vertices U and V in this graph G. So in this graph G, we are going to take two adjacent vertices. Adjacent vertices means what? If we take two vertices, when are these two vertices said to be adjacent? If they have an edge between them. For example, if you take this as U and this as V, if there is an edge between them, these two vertices are said to be adjacent. So we are going to take two vertices which are going to be adjacent in G. So I have written that here. Now in this graph G, we are going to form a, from this graph G, we are going to form a subgraph. So subgraph that we are going to form newly, we are going to represent it as G dash. So this subgraph, so the subgraph we are going to form newly now. And how are we going to form it? This G dash, we are going to remove the points U and V from G, and we are going to consider the remaining graph as G dash. So from G, we are going to remove the points U and V. So the edge between them will also be removed, and the remaining graph we are going to take as G dash. Now we know that the graph G has 2n plus 3 number of points. From those number of points, if you are going to remove 2 points, you have to subtract 2 from this value. So G dash will have, so this has how many vertices now? So for G has 2n plus 3 vertices. From that we are removing 2 vertices U and V. So minus 2 points it will have. And it will have no triangles also. That also we should mention. So G dash finally how many vertices it will have? 2n plus 3 minus 2. That will be 2n plus 1. So that we will write. So G dash. Okay, this new graph. After removing the 2 points, we get this. So G dash has 2n plus 1, because 2n plus 3 minus 2 is 2n plus 1 points. So these many points it will have, and it has no triangles. So that also we should mention. Now after removing these 2 points, what is happening? We are getting 2n plus 1 points in G dash. But we have already assumed from our assumption. What do we assume? Let us assume that the result is true for all values of p lesser than or equal to 2n plus 1. So we assume that the result is true for this, which means it will satisfy the given result. So hence by induction hypothesis, what we will have? The result will hold according to induction hypothesis. That is, the number of edges of Q of G dash will be either lesser or equal to. So the maximum number of edges will be p squared by 2, because the result will hold. But what is p now? 2n plus 1. We will substitute that. So integral part of 2n plus 1 the whole square divided by, it is actually 4. Okay, by mistake I wrote 2. It is 4. So divided by 4. So now this will be equal to, that is, it's going to be equal to, for the, see, now a plus b the whole square formula we can use, and we can split up this. So a square, which will be 4n square plus 2ab. So 2n in, multiplied with 2 is 4n. So it will be 4n plus 1 square is 1 divided by 4. So the integral part of this. Now in this, we can take this denominator 4 to each of the terms separately. So first term, if you take 4n square divided by 4. So 4 will get cancelled. So you will have n square. Plus the second term is 4n divided by 4. Again 4 will get cancelled. So you will have n plus 1 by 4. Now what is the integer here? This one. So we can remove this integer because we are taking only integral part. So after taking the integral part, you get this to be equal to n square plus n. But actually it is lesser than or equal to, no, so that inequality we have to bring here. So lesser than or equal to n square plus n. So therefore q of G dash is lesser than or equal to n square plus n. And let us mark this as equation 1. Okay, now next. So after marking this as equation 1, we are considering another one point, that is, since G has no triangles, we know that the graph G has no triangles, and G dash is a subgraph of G. So no point of G dash can be adjacent to both U and V in G. So we know that U and V are adjacent to one another, U and V. So now if there is another point in that graph, now this point can be adjacent to any one of these two vertices only. It cannot be adjacent to both the vertices at the same time. Because now if, for example, if these two vertices are adjacent, if this is W adjacent, this is possible only when there is no edge between U and W. Because if you form an edge, it will become a triangle, but we know that there are no triangles in G. Therefore, if you take one point in G, it can be either adjacent to U or it can be adjacent to V, but it cannot be adjacent to both U and V. That only I have written. Since G has no triangles, no point of G dash can be adjacent to both U and V in G. So let us mark this as equation 2 because we are going to make use of this 1 and 2 now. Now the lines of the graph G will be of three types. The first one is lines of G dash. So we know that that is just now we saw that the lines of G dash is Q of G dash, which is lesser than or equal to n square plus n. So from 1 we can say that the lines of G dash, that is Q of G dash, is lesser than or equal to n square plus n. This is from 1 which we found just now. This one, it can be one of this type. And the second type is lines between G dash and UV. That is the lines between the subgraph G dash and the removed vertices UV. So that is from 2 we have obtained. That is here. So from 2, since G has no triangles, no point of G dash can be adjacent to both U and V in G. Which means that these are the lines which are lesser than or equal to 2n plus 1, which we assumed previously. So that only. So lines between G dash and UV is that which is lesser than or equal to 2n plus 1. This is from 2. And then the line UV. So how many? There are the two vertices U and V has one edge between them. So this is 1. So these are the three types of edges that we get. So now therefore how the edges of G will be? So hence the edges of G will be Q, because G has Q number of edges, and that will be lesser than, so that is lesser than or equal to, the first one is n square plus n. So n square plus n. Okay, this one. And then 2n plus 1. So we will add that. So plus 2n plus 1 and then 1. So we will add this 1. So now on simplifying, this will be equal to n square. N plus 2n is plus 3n and plus 1 plus 1 is 2. So therefore Q is lesser than or equal to n square plus 3n plus 2. Now we want to bring it in the form of p square by 4. In this form we want to bring it. In order to do that, we will multiply and divide this by 4. So Q will be lesser than or equal to, if we multiply by 4, it will be 4 into n square plus 3n plus 2 divided by 4, which is equal to 4 multiplied with n square is 4n square. 4 3 times is 12, so plus 12n, plus 4 2 times is 8 divided by 4. Now we want this in the form p square. We want to write it in this form. So in order to bring it in that form, we can try to bring it into a perfect square by adding and subtracting the square term. We know that how to make it a perfect square. So in order to make it a perfect square, so this will be equal to, this 4n square can be written as 2n the whole square plus 2ab. So a is 2n. So 2 multiplied with 2n. And so the remaining will be from 12n, we have 4n here. 4 multiplied with 3 is 12. So multiplied with 3. Now this is like a square plus 2ab. So b is what? 3. So b square we have to add. So 3 square. If you are adding it, you have to also subtract it. So minus 3 square and then plus this 8. The whole divided by 4. In order to make it a perfect square, we are doing so. And so that will be equal to 2n the whole square plus 2 and then 2n multiplied with 3 plus 3 square. But what is this? This is 2n plus 3 the whole square and then minus 9, because 3 square is 9, plus 8 the whole divided by 4. Now combining these terms, we can write it as 2n plus 3 the whole square and minus 9 plus 8. So it is minus 1. the whole divided by 4. Now we want, we can divide the denominator. So this will be 2n plus 3 divided by 4 minus, separating the denominator, 1 by 4. But when we take the integral part of this, this fraction will be negligible. So because we are going to take the integral part, so therefore q will be lesser than or equal to the integral part of 2n plus 3 the whole square. Okay, I missed the square here. The whole square divided by 4. So we have brought it in that form. So p squared by 4. But what is the p actually? So we have taken p here. P is equal to what? 2n plus 3. So this 2n plus 3 can be written as p. So therefore q is, from this we get q is lesser than or equal to integral part of p square divided by 4, because 2n plus 3 is p. So we have proved the result. Also we will consider for a particular value of p, that is, so also for p equal to 2n plus 3, we can rewrite this as, see this 2n we can write it as n plus 1, because n plus 1, so what will be remaining? N plus 2. So I am just splitting it so that I can get a complete bipartite graph. That is, I am splitting this 2n plus 1 as n plus 1 number of vertices in one set and n plus 2 number of vertices in other set. So what we will get? We get a complete bipartite graph, that is with k n plus 1 number of vertices in one set and n plus 2 number of vertices in another set. So we know that in a bipartite graph k m comma n, the total number of edges will be mn. We have to multiply this m and this n. So because it's a complete bipartite graph, so total number of edges is mn. So therefore multiplying these two, we get the number of edges for this bigraph, and obviously a bipartite graph will not have a triangle. And then n plus 1 multiplied with n plus 2 lines we have, because for a bipartite graph mn is the number of lines. Therefore m here is n plus 1 and n here is n plus 2. Multiplying these two, we get the number of lines. So when we multiply n plus 1 and into multiplied with n plus 2, what we will be getting? N squared plus 3n plus 2. So which is equal to what? P squared by 4 number of lines by this, because just now we got it. We had n squared plus 3n plus 2 and we got it as q lesser than or equal to p squared by 4. Therefore, in particular, for one particular value of p equal to 2n plus 3, we get it to be equal to p squared by 4. So we have proved the lesser than inequality and we have also proved the equality. So hence the maximum q is attained. So I have written that. Hence the maximum q is attained. Now remember, we have completed only the proof for odd number of vertices when p is odd. In the same way, we have to prove for when p is even. So I will show you that. So now part 2 is for even p. First, in the same way, we are going to assume that the result is true for all even p lesser than or equal to 2n. Because how the even numbers will be, it will be 2n and then 2n plus 2, the even numbers will be of this form. So because when you give value for n over here, for example, if you give n equal to 1, you get 2. N equal to 2 means 4, which is an even number. N equal to 3, it is 6, again an even number. Similarly, here also if you give n equal to 2, 4 plus 2 is 6. So you get even number. So as you keep on changing the values of n, you get even numbers. If you give n equal to 1, it is 2 plus 2, which is 4. So these are the generalized form of even numbers. So we are going to assume that the result is true for p lesser than or equal to 2n. And we are going to prove that the result is true for p equal to 2n plus 2. So by the method of induction, we are going to prove this. And obviously we consider that there are no triangles. So the same how we proved for odd p, in the same way we are going to prove for even p. So in the same way, we are going to consider a graph G. Now here it is even, no. So with p equal to 2n plus 2 number of vertices and no triangles. And as before we saw, if q is equal to 0, then the result is true. Hence we are going to take all values of q to be greater than 0. So now what we will do, we will consider u and v adjacent pair of vertices in G. So we will write that step. Then what we will do, we will consider a subgraph G dash by removing the vertices u and v from the graph G. So that step we will write. So as I told you, we have taken u and v to be pair of adjacent vertices in G. Now we are forming a subgraph G dash after removing U and V from G. So we know that G has 2n plus 2 number of vertices. If you remove 2 vertices from that, so minus 2 points you will have. That is, G dash will have 2n plus 2 minus 2 is what? 2 and 2 will get cancelled, and so remaining will be 2n. Therefore, the subgraph which we form will be G dash, and it will have 2n points and no triangles. Now by induction hypothesis, we know that the result is true for 2n points because of our assumption. We assumed that the result is true for all those values of p lesser than or equal to 2. So therefore, by the induction hypothesis, we can write that. So by induction hypothesis, we know that the number of edges of G dash will be lesser than or equal to p square by 4. But what we have obtained it to be 2n points we are having. The value of p for G dash is 2n. So when we substitute, it will be 2n the whole square. So which will be 4n square divided by 4. And so 4 will get cancelled, and the integral part of n square is n square only. So therefore we obtain q of G dash to be lesser than or equal to n square. Now let us mark this as equation 3. Now already we have 2 and 2. Now this has 3. So therefore we will write the 3 types of lines of G. That step we will write now. So as we saw in the previous odd case, now in even case also the lines of G will be of 3 types. First is lines of G dash, which is what here only we obtained, q of G dash to be lesser than or equal to n square. So from 3. And lines between G dash and UV, just previously we saw from 2 it will be lesser than or equal to, here the now assumed lines is 2n, so it is 2n. And the line UV is 1 because it is one edge. Now what we should do in order to find the lines of G, we have to add all these 3. So let us do that. So hence we have q to be lesser than or equal to n square plus 2n plus 1, because we have added all the 3. First was n square, then 2n, then 1. And this is what actually it is, n plus 1 the whole square. So q is lesser than or equal to n plus 1 the whole square. Now we want to bring it in the form p square by 4. So for that we should multiply and divide this by 4. So q will be lesser than or equal to 4 multiplied with n plus 1 the whole square divided by 4. So this 4 when taken inside the bracket, it will become 2 multiplied with n plus 1 the whole square. So it can be written like this. Okay, and divided by 4, and so that will be equal to, when you multiply this 2 inside, it will be 2n plus 2 divided by 4 the whole the integral part of this, and this is square. Therefore we get q to be lesser than or equal to the integral part of 2n plus 2 the whole square divided by 4. But what is 2n plus 2? We have assumed it to be p, so that's equal to integral part of p square by 4. So therefore we have obtained q to be lesser than or equal to the integral part of p square by 4. Hence the theorem holds for even p also. So hence the theorem holds for even p also. Now for particular one value of p which is equal to 2n plus 2 we should take, and it can be partitioned as n plus 1 vertices, where it will be like k n comma n, where the first set has n plus 1 vertices and the second set also has n plus 1 vertices. So it's a complete bipartite graph, and it will have no triangle of course. And what I told you, how the vertices will be, it is n into m. The number of edges will be n into m. So here n is n plus 1, m is n plus 1. So when you multiply, we get the number of lines. But what is n plus 1 multiplied with n plus 1? It is n plus 1 the whole square, which is equal to n plus 1 the whole square. And obviously we have already proved that it is equal to integral part of p square by 4. Just now we proved it here, because when it came as n plus 1 the whole square, we have proved that it is p square, integral part of p square by 4. And so here also it holds. Hence this maximum q is attained. So hence we have proved this theorem. Hope you have understood this theorem. And this result is a very significant result in the examination point of view. So kindly go through it very patiently. Surely you will understand. And the proof for odd p is same as for even p. So both are similar proof. The only difference being there it is 2n plus 1 and 2n plus 3 since it is odd. and here it is 2n and 2n plus 2 since it is even. So it will have likes of proof only. So kindly go through it patiently. Thank you.